Section 5.5, Property of Logarithms. Let's recall if we had to solve the problem log base 3 of 3 to the x equals 1 to find x, right? We could rewrite this, right, in its exponential form. We have our base 3. We know that the log is the exponent 1 to get 3 to the x, right? So we could rewrite this equation in this manner, and we would know now that 1 is x, right? So I'm going to plug this in. We see that log base 3 of 3 to the first is equal to 1. So basically we're noticing that we take the log of a function with the base that has the same base as the logarithm, you get the exponent on the base back, right? So this 1 and this 1. Why? Well, what the deal is that we're actually composing the logarithm and the exponent. We're composing two inverse functions. Let's look at it more generally. Let's say instead of base 3, we have base a of a to the x, and it equals x, and we want to know what x is, right? Well, let's let f of x be log base a of x. That's one function. And we're going to let its inverse, which we know is a to the x, right? If I take f and compose it with its inverse, right? That's f inverse of x, right? That will be f of a to the x, and in taking a to the x, I say I'm going to plug it into my f, which is log base a, anywhere I get that, anywhere I have x, right? And we know that if you compose a function with its inverse, you always get x, right? That's the definition of, or that's the, not the definition, but that's what always happens for inverse functions. So notice, this is what we had to evaluate originally. It ends up being equal to x because we know they're inverses. Okay? All right. Well, this is one property of logarithms, and we're going to look at a lot more. These properties of logarithms are on page 302 of your book, and you'll need to memorize them. Okay? Page 302 in the book. We're going to do a lot of work with them, so they'll be pretty simple to memorize just because you're going to use them. But you do have to memorize them. Okay, the first property is that the log of any base of 1 is equal to 0. Why is that? Well, if we take a and raise it to the exponent 0, remember the log is the exponent, any base to 0, exponent is equal to 1. Okay, the second property, log base a of a equals 1. Why is that? Well, if I take the base to the exponent, or the log is the exponent, a to the first is equal to a. The third property says that log base a of a to the r is equal to r. That is what we just showed, right? Because we're composing all of the, we're composing the logarithm with its inverse function, the exponent. Okay, so we're going to say composing inverse functions as the reason for this. Okay. The fourth property is composing the other way. We're going to say if we take a to the log base a of r, we're also going to get r back, right? So this is composing inverse functions the other direction. Notice we're taking a logarithm and plugging it into a to the x, right? And so we get that r back. All right, the next property, very useful, log base a to the m times, log base a of m times n. it turns out that this is log base a of m plus log base a of n. Well, why does this work? Yeah? Let's take a look at a little proof of it. Okay? We're going to call the log base a of m, we're going to call it big A. If that's true, oops, then it's also true that a to the small a to the big A is equal to m by the definition of logarithms. And we're also going to let b equal log base a of n. So it's also true that a to the b equals n. Okay, now let's take a look at what we're starting with. So we know that log base a of m times n is the same thing as log base a of a to the a times a to the b, right? We're just substituting in. We know by laws of exponents that if you raise the same base to exponents and you're multiplying them, you add them together. So that's a to the a plus b. And then if we look back and we say, oh, let's look at this property 3 up here, right? This whole thing then is equal to a plus b. Well, what was a? A was log base a of m, and b was log base a of n. Sorry, not b, n. Okay? So in all, we get that log base a of m times n is equal to log base a of m plus log base a of n. Okay? Similarly, we have another property that says log base a of m over n equals log base a of m minus log base a of n. I'm not going to do that proof because you can read it in the book. And it's similar to the proof of number 5. And the last one, I am going to show you the proof of this. Log base a of m to the r equals r times log base a of m. This is a very interesting one and maybe kind of surprising. Notice what happens. This exponent here kind of floats down and around to the front, and it becomes a factor times the logarithm. It's no longer an exponent, it's now a factor. Very interesting. Alright, well let's look at that proof, because how does that work? Well, let's start with log base a of m to the r. Okay? Now, again, we're going to use the fact. We're going to let a equal log base a of m. Okay, we're going to use a little substitution. Okay? And remember what that means? That means that a to the big A equals m. Okay, so let's hold on. I'm going to erase this and move over a little. All right, let's go ahead and start again. We're going to say log base a m to the r. So if we plug in for m, that's log base a of a to the a to the r. So all I've done is substitute m for its value. We know that if we take an exponent and raise it to another exponent, we get a to the a times r. And then if we apply property 3, again, let's go back and look at property 3, right? This one that I have underlined in green. Yeah. We know that this whole thing is going to be equal to AR. Well, AR is the same thing as R times A, isn't it? What was A? Well, A was the log base A of the m. So notice that exponent became a factor times the logarithm. That one is really incredibly useful. You're going to use it all the time. Okay? Let's use these properties. All right. The first thing we're going to do is we're going to write each as a sum or difference of logs, and we're going to express exponents as factors. Some books call this expanding an exponential expression. Okay, so we're going to take log base 3 of x over 9. Well, based on property 6, we know that we can then say, oh, this is log base 3 of x minus log base 3 of 9. Yeah. Now, anytime you're doing this, if you can evaluate a logarithm, you go ahead and do. So log base 3 of x, I can't evaluate that. But what's log base 3 of 9? Well, it's the exponent that we raise 3 to get 9. It's 2. Okay. All right, let's do one more problem over here. We're going to take the natural log of x times e. Now that we know what natural log is, we can use it all over the place. Again, if I multiply two things and take their log, that's the same thing as taking the sum of each log separately. I can't evaluate natural log of x, but what's natural log of e? Well, it's 1, right? Because the exponent that we take e as a base to raise it to get e is 1. All right, we're going to do one more in this direction, and then we're going to start talking about compressing. Although we're going to find out something kind of cool in the meantime. We're going to take log base 2 of the cube root of x squared plus 1 all over x squared minus 1, where x is greater than 1. Okay, well, the laws of logarithms say, okay, I'm dividing two things and I'm taking their log, so I can separate that up as the log of the numerator minus the log of the denominator. Okay, and I want to write exponents as factors. So the first thing I need to do is realize that the cube root is the exponent 1/3. Okay, and then I'm going to bring it down and around using that last law of logarithms to make it a factor. Okay, are we finished? We are. Beware. Be very, very careful. We cannot take this log base 2 of x squared plus 1 and separate it up. A lot of people make this mistake when they're first learning about logarithms. They think that they can distribute the log, right? It's not, the log itself is not a number. It's a function. You're taking the logarithm of something else, right? So you can't actually distribute it. And remember that the property actually says that log base 2, or any base, of a times b can be separated up into the sum of the logarithms, right? It's not if you're adding something and taking the logs. It has to be multiplication. So why is this equation, I'm sorry, not equation, why is this expression say that x is greater than 1? Interesting. Well, let's recall something for a second. Let's recall we're going to look at the exponential function, f of x equals 2 to the x. It goes through 0, 1, and 1, 2. It also goes through -1, 1/2. Okay? So if we're going to look at the logarithm with base 2, right, what we want to do is flip that over the line y equals x because it is the inverse function. It's then going to go through points 1, 0, 2, 1, and 1/2, -1. I'm just flipping all the x and y values. Alright, here it is. This is I'll call this g of x equals log base 2 of x. Notice that the domain here, because we have the y-axis being a vertical asymptote, it's all x such that x is greater than 0. Okay? So this is a really important thing. The domain of f of x for any base, logarithm function with any base, is all x such that x is greater than 0. So it turns out that you cannot plug a 0